Welcome. In this video, we will explore how to simulate and analyze the forward kinematics of 3-DOF robotics arm using Python and PyBullet. In this experiments, help us understand the spatial limits of robots' joints before deploying them in real-world environment like surgical units of assembly line. I am Tehnu from MTech Embedded System under the guidance of Dr. Dhanalakshmi, Professor of ECE Department and SRMHT. Okay, let's see. The aim of the experiment is to determine the maximum and minimal position of each links in a robotic manipulator using a forward kinematics. We use PyBullet for a physical simulation for like a NumPy for the computation and Matplotlib for a 3D plotting. Okay, let's explain the code. In this, we will begin by importing the required Python libraries like PyBullet and PyBullet slash data are used for the physics simulations and accessing a robot models. In this, NumPy helps to generate the angle values for the joints. Panda is used to create the table of results, and Matplotlib library allows us to plot the 3D movement of the robot joints. Okay, let's here we connect the PyBullet simulations to in the direct mode, which runs without the graphical windows. We also set the path to access built-in URDF files like KUKA model. The robot is loaded with the fixed base, so it does not move during simulation. And load KUKA IVAR robot is used to the load for the robot is fixed to the base. It won't move around. And next, data containers. In this, we will initialize three dictionaries: minimum position and maximum position. We'll hold the smallest and largest XYZ position E recorded by for each joints. Joint parts will be stored the path traced by the each joints during the simulation, which will use for the 3D plotting, and they will be later. For the every joints, we will vary angle from minus 2.5 to plus 2.5 radian using no line space. We loop through each joints of the robot. For the every joints, we create the three empty list to the store the x, y, z and position that it visits during the angles web. For the each joints, we iterate through 15 different angles ranging from minus 2.5 to plus 2.5 radians using a NP line space. The reset joint states functions update the joint angle like step simulations runs the physical updates, and getLink states retrieves the 3D position of the joint link. Here we are append the XYZ coordinates of the joints to the joint points dictionary. This data is used to later the visualizing the 3D trajectory of the joints. If the joints being recorded for the first time, we are initialize its minimum and maximums with the default extreme values. This allows to start tracking the true minimum and maximum later. For the every coordinators x, y, z, we update the minimum and maximum values encountered during the angle swap. This helps to define the motion limits of the each joints. After the simulation, we will round of all values to two decimal place for easier readability and store them in a list along with the join numbers. We create the pandas data frame to neatly present the minimum and maximum XYZ position for each joint. Its outputs helps to understand the spatial limits of the robot movements. Now we have prepared the plot the joints of the path in 3D. We will create the 3D figure and the subplot for 3D plotting and choose the color map, and each joint's path has been different colors. And all joints parts are plot x, y, z coordinates using colored lines. Each line represents the trajectory of one joint, its angle of changes. And finally, we added the label of axis and legends to the identify the each joints. Then we will show the 3D plots. In this process, clearly illustrate how the different joints contribute the overall movement and workspace of the robotic arm. Okay, let's run this in Google Colab. and was successful. Let me explain the table of joint position. Let's take joint 0. It coordinates the x varies of minus 0.032 plus 0.3. Y goes from minus 0.032 plus 0.02. Its z stays fixed at 0.28, indicating that mainly rotates the horizontal circle close to the initial height. And joint 1 shows the slightly larger range with the z increasing up to 0.42. It tells joint 1 helps to armed upward, contributing the vertical motion. Joint 2 has been border x and y ranges and z goes for the 0.6, and also it suggests the contributes to the both horizontal reach and elevations. Joints 3 and 4 for their position for the tidy clusters. Then closer to the end effector, but their z-axis reaches up to 1.03, the highest point in the entire robot motions. It indicates they are involved the fine tuning the reaches. Joint 5, it's interestingly dips into negative z values going to low as minus 0.42. This means part of arms and end effector can be below the base level for face bending down or backward. Joint 6. The last joint shows the widest spread overall from minus 0.92 plus 0.72 in X and from 0.48 to 0.46 in Z. It reflects the flexible precision positioning needing by the end effector of the gripper. Let we go for 3D path tracing. Plot shows how the each joints of KUKA robots arms are moves in the space with its angle change. Each colored lines represents the movements of one joints in the 3D with the x1 side axis showing the points joint 0 and base creates the wide arc showing base rotation joint 1 joint 2 and arms upward and outward, while joints 3 and it shows small tight loops near the ends which are used to precise control. This helps to understand how the each joints contributes to the arm's motions and shows the overall space the robot can reach. That's all about it. Thank you guys.